Okay, so I wanted to go over the bit that you guys might have missed today. This starts at the bottom of, I forget the page number, but I think you guys could find it in your guided notes. But we've been talking about both the two different things that can happen when something absorbs heat. It can either change its temperature without a phase change, or it can change its phase without a temperature change. All right, so how are these related? If you are near or at the melting or boiling point, say for instance you're at 0 degrees and you're a piece of ice and you absorb some heat, your phase is going to change. You're going to melt. But if you're not near the melting or boiling point and you absorb some heat, your temperature is going to change. All right. So all of these things can be kind of tied together in what's called a heating curve. All right. So, and what this is going to do is show what happens to the temperature of a substance when it absorbs heat. And the most famous heating curve is going to be that for water, and I've shown it here. You can have a heating curve for any substance, but the similarity with other substances is that the overall shape is going to be the same. It's just that the temperatures, the locations of the temperatures is going to be different. So the way this is going to work, first of all, on this graph we have temperature right here on the y-axis. We're going to put either heat absorbed or time of heating. They basically mean the same thing. Pretend that you put a candle underneath of an object. All right, the length of time that candle stays under the object, the more heat it's going to give to whatever is on top of it. So either way you think about this would be fine. All right. So what we're going to do here is let's pretend that we have some ice in a cup, or some water in a cup, and we put it in a very, very, very cold freezer. All right. We could get it down way below 0. All right. So let's say that we got it down to about -80. All right. So let's say that we took that block of ice and we put it out on the counter. All right. So obviously that that block of ice is going to start to absorb heat from the warmer things that are around it. All right. So what's the first thing it's going to do with that heat? All right. A lot of times people say, well, it's going to start to melt. All right. The thing is, if that block of ice is at -80, it first has to warm up to the melting point. All right. So the first thing that it's going to do with heat is the temperature is going to rise. It's going to cause, you're going to go from a really, really, really cold block of ice to a block of ice which is at 0. All right. At that point, the temperature of that block of ice, of that water, is not going to keep going up. And that's because it's going to be undergoing the process of melting. All right. Remember, when something is changing phases, the temperature stays the same. All right. The heat that gets absorbed goes towards changing the phase of the material. All right. So a way that you could think about this is at this point right here, it's when you first start to see a little bit of the water form on the ice. All right. So it's the first drop of liquid water that you would see. Right. And as you keep on going this way, the bits of ice get smaller and smaller and smaller, but still the temperature of that ice water is 0. All right. So this point right here would be when the last little bit of ice melts. All right. At that point, the temperature of that water is going to start to warm up. All right. You're going to go from having cold water to having warmer water. All right. And that's going to keep on going up and up and up. So once you get to room temperature, in order to give that water more heat, you would have to put it on some other heat source like a stove. So as it continues to absorb heat, the temperature is going to continue to go up. And it's going to go up until you hit 100 degrees. And what's going to happen there is it's going to start to boil. All right. A lot of times I'll ask people, which has got a higher temperature, water that's been boiling for 5 minutes or 10 minutes? And they'll say, well, for 10 minutes. All right. The thing is, if water's boiling, it stays at the same temperature. All right. So it doesn't matter how long it's been boiling. As long as it's boiling, it's going to be at this temperature. All right. So the difference between this point right here, that's going to be when it first starts to boil. All right. And as it boils, you'll notice that the water level goes down. All right. If you put a pot on the stove and you forgot about it, you'd notice that the water level goes down, down, down until the point when the last little drop boils away. That's when you'd be right here. All right. Well, if we could capture the steam that had boiled off, all right, you would notice that if that is continued to be, if you continue to heat that, it's going to continue, its temperature would continue to rise. All right. So what we're going to do with this is, I'll make an analogy here. Let's say that you're driving on a road. That's, first of all, it's kind of flat like this, and then you got to go up a hill like this, and then you got to go on this section right here, and then you got to go on a section right here. And I said, well, how much gas would it take to get from here to right here? Well, the thing is, you're going to be burning gas in different ways. You burn gas differently on a flat area as opposed to a steep hill. All right. So in order to figure out the amount of gas you'd burn from here to here, it's not just going to be one step. You would have to calculate the amount of gas you'd burn on this section, plus the amount of gas you'd burn on this section, plus the amount of gas you'd burn on this section, plus this section right here. All right. So what we're going to do here is we're going to try to answer a problem like this. Well, let's say that you had a 50-gram block of ice that was at minus 78. How much heat would it take to completely melt that and allow it to allow it to come to room temperature? All right. So just take that minus 78 block of ice, put it on the counter, and just let it absorb heat. All right. How much heat is it going to absorb? All right. Well, let's take a look where we're starting and where we're ending. All right. The starting point would be about right here. That would be about minus 78. Okay. So what's the first thing that block of ice is going to do? The first thing is it's got to warm up. It's got to absorb some heat until it gets to the melting point. All right. So as far as the total amount of heat, the first thing that's going to happen is this part right here. So remember, when something is staying the same, sorry, when its phase is staying the same, but its temperature is changing, the equation for that is mCp delta T. All right. So that's why we put this part right here. And what that's going to describe is the warming of the cold ice. All right. The next thing that's going to happen is the ice is going to melt. All right. So that's what is going on right here. And the equation for that is MHF. Remember, you can use Q equals MHF for both melting, which would go from left to right here, or for freezing, which goes from right to left. All right. So that's what this part is right here. Right. That's the amount of heat that ice would have to absorb to just do the melting part. All right. Then after the water melts, you've got 0-degree water. That 0-degree water would then absorb heat until it becomes room temperature water. We're going to assume that room temperature is 25 degrees Celsius. So the equation for this part right here is going to be mCp delta T. So we're going to put that in right here. So just want to point out that this part right here looks just like this part, but there's a difference. This is Cp is the specific heat. All right. This would be the specific heat of ice. All right. Remember, the specific heat depends on the state of matter. All right. So this right here would be the specific heat of water. All right. So filling in. So the reason that there's 3 parts to this is that there's 3 different parts when this thing is warming up. If we had gone farther, there could possibly be up to 5 parts to this equation. All right. So filling in, m is the mass. That's 50 grams. The specific heat of ice is 2.05. And what's the temperature change? All right. Notice we're not doing the temperature change from minus 78 to room temperature. We're just doing the temperature change for this part right here. So what is the difference in temperature from minus 78 to 0? All right, that's 78 degrees for that part right there. All right, that's why we're going to put 78 right there. Again, plus the mass, which is 50, times the heat of fusion, which is 334 joules per gram. Notice I'm leaving out the units here. I'm doing that to save a little time. Technically, I should be putting the units in, but I want to move along a little quicker. All right, and then the last part, the mass, 50 degrees. CP, notice that I now use 4.18 instead of 2.05 because this is the specific heat of this material, which is liquid water, and that's going to be 4.18. And what is the delta T? What is the temperature change from 0 up to 25? Right, that's 25 degrees. We put that in. You do all this, calculate your answer. That would end up being the total amount of heat to get from here to here. All right. One thing I want to point out: if you are relatively comfortable with math, notice that when you're doing this equation right here, there's m in each of these terms. All right. And if you remember from math, if you've got the same variable in each of these terms, you can do what's called factoring out. All right. So I'm going to take m and I'm going to put in parentheses what I have here, Cp delta T, HF, and then this part right here. All right. Remember, the opposite of this is when you distribute. All right. I could turn this back into the original equation by distributing the m to all of these terms. All right. This is just the reverse of that. The reason that you might want to consider doing this, if you have, when you're done, you've got to put all these numbers in your calculator. All right. You'll do less button pushing on your calculator if you factor out the mass. All right. Either way is fine, whatever you're comfortable with. Just make sure that you get the right answer when you're done.